In the last 12 months, there's been an outbreak of avian influenza in cattle in the US, and this has badly affected milk production and has some possible consequences for allowing the transfer of bird flu into mammals and therefore into humans. What I want to do is construct a phylogeography which shows how it's spreading between the states, so that I can look at where it originated and what is the medium that it's spreading through. So is it going from one cow and one farm to another farm, or is it going from cattle to birds and then back from those birds into cattle again? I'm going to follow the tutorial on how to do a phylogeography using Beasts, what was written actually quite a few years ago in 2016 by Remco Beauti, and it's based on ideas that were created by Patrick Lemmy and co-workers in 2009. This uses the Beast package and a coalescent model to construct the phylogeography. You need to have tracer so that you can check that you've got convergence of your simulations, and fig tree to look at the output as well as spread for looking at the geographic spread as a KML file, which can then be displayed on Google Earth. You can also use the KML file within R, because there are R links to KML files. And the process is you have to start with an alignment. If you've got a smallish alignment, I would align with muscle if you've got a limited number of sequences. For a larger number of sequences, considering these are viral sequences and all very similar to each other, MAFT will do a perfectly fine job in a reasonable amount of time. When you do the alignment, you still need to do some editing to make sure that you haven't got sequences with missing nucleotides, so large numbers of ends. And in this case, because we also need the geographic data, you need to remove any sequences that do not contain geographic data about the state they were located in. So any sequences that found that say yes, this comes from the US isn't useful, because we need the exact location regarding the state to be able to use it in this particular analysis. As always, to set up the particular run, you use Beauti. So here I have a set of files, and actually you can, and I've got the original sample and I've got the sample aligned. This is from the NCBI database, where you can ask it to generate a sample of the data. So it's created a sample of 100 random sequences, which after I aligned it and removed any problem data, went down to being 91 sequences. So this is the alignment that I'm going to use within Beauti. I've put the Beast 2 installation actually as a subfolder of this folder that I'm working in, just to make it easier for me to locate. So if I go into there and I find Beauti, what I need to do first thing is import the alignment. So import the aligned things. The nucleotide sequences, so that is done. Next, I need to extract the tip dates, because I'm doing a coalescent based model. Now if you look at this starting thing, the format is for the dates is year, month, day. So I need to change the format here to year, month, day. It is then in, this is the first field before a vertical line, this is the second field between these two vertical lines, and this is the third field. So I need to auto configure to look for the first vertical line, and I need to take group 3. Press OK. So I can see here, this is the raw date value. They'll be dated so that the most recent sequence is called 0, and then any time before that will be in fractions of a year. So anything that's 6 months ago happens to be 0.5. The other ones are harder to understand, but they're fractions of years in terms of 365 days. And then we need to think about the site model. Now, I'm definitely not going to use Duke's Cantor, but what is the model that I wish to use? So if I go back to my file, my aligned file, and I open it in Mega and I want to do an analysis of it, press OK. Yes, it's protein coding and it's got the standard coding. So what I can do is a model test within Mega to find out which model is going to be most effective. Now the tutorial suggests HKY with gamma substitutions, but I'm going to run through this and see what is better. The model also allows for invariance if you want to. So here, the top two models are HKY and HKY plus I, which is invariant. The difference in Akaiki's information coefficient is 7. I'm trying to figure out whether I think that is a large enough thing that I want to make any differences. Anyway, I'm going to use the HKY model. I can or cannot use invariant. None of the gamma substituted models come up particularly well. They're all down here and they are very significantly different to these models, so I'm not going to use a gamma, even though it's suggested in the tutorial, because I don't think it's necessary in this case. So I'll switch this to an HKY model, leave the kappa as is, gamma count as 0. I could set that to 0.8, what's the value, 0.81. If I set it, it will make the convergence of the model faster. So it is a good idea to put these things in when you can. So frequencies need to be empirical, not estimated. That's also mentioned in the tutorial. The tutorial puts a clock rate of 0.004. I run this simulation before, and 0.004 is the thing that you're going to end up with at the end. You can't know this for sure. The virus is going to evolve in a similar rate to the virus in the tutorial because it's the same virus. The tutorial is based on flu, and this is still flu evolving. So it happens that 0.004 is a useful parameter, but probably you need to run the simulation at least once to find out what's a useful parameter, and then you can try and optimize it. Otherwise, just leave it at 1 and let it estimate it. It just takes longer to do. Now, because we've got tip dates, this has got a red dot beside it because you can't use the Yule model, because it's not, the Yule model doesn't take into account tip dates. So we need to do coalescent. Now it's coalescent with a constant population. Why a constant population? It's because the population is an effective population. It is not the population that you see. So it's not the thing you're measuring. It's not you saying, well, you've got more cases of flu as it goes up and you get an increasingly wide outbreak. That's not what it's meaning. What it is meaning is, what is the effective population in terms of the size of population that's creating mutations? So the rate of mutation and the population are two parameters that are linked together intimately in the equations, which determine how rapidly something's evolving. And you can't really separate the two. So this is not going to be a real population. It's going to be an artificial number in the population. And that's the first part of it set up. Now we need to go back to partitions. If I drag this out a little bit, it's still not worked. So I wish to see Okay, I need to slide down. Now I want to add another partition, and it's on this little plus button at the bottom, which is not immediately obvious. So if I hit plus, I can add a continuous geography, which I don't want to do because I've got discrete geography talking about the specific locations. If I was looking at something evolving within a single region, and I wanted to look at very precise evolution across the geography, then I could probably do the continuous one. But I'm going to add a discrete trait instead. Now the new trait I'm going to call location. I was going to say state because I'm using US states, but state has a specific meaning in MCMC calculations, so I'm not going to use it. So I'm going to use location. Now it's a discrete thing I want to guess. Now the discrete thing that I'm guessing is in this second column. So I want to do a guess. Again, I want to split based on the vertical lines. I want to take group 2 this time rather than group 3. And then I have these traits. So this is all of the different states. Close. Now, once you've created location, so location also has a site model, which you don't want to do anything with. Location also has a clock model. I'm going to make this the same as the other one. And location will have some extra priors. Now, because I've done this calculation right, I've set this up right. I've not got an extra box that pops up here which says, do you want to use a Yule model to model your other partition? Now, if you get that, then you've done it wrong. I've done this right because I didn't get any extra boxes in this particular priors thing. So I know that this is going to work. If I'd got another line in here which says Yule model, then I've done something wrong and I need to go back and edit the file until I've got consistency. Do I want to change the MCMC parameters? Probably not in this particular case. So I can now save this particular thing, which I'm going to save it as Phylogeography.xml and save. I happen to have one there that I prepared earlier and didn't work. And then I exit and it says yes, I'll save it again. Save. Right, I'll replace it. It's done. So now I've got my file that I can run into Beast. So I can close Mega, close that, saving. So if I go into Beast 2, I open Beast, choose my input file, and it runs perfectly. 2 minutes per million samples, so I let that go and see what it's going to do.